Hi, we are from Group 7 and our presentation is about hydrogen production and bioelectrochemical system with a focus on microbial electrolysis cells or MECs. These are our team members. The growing global demand for sustainable and renewable energy has intensified the focus on hydrogen as a clean and efficient energy carrier. Hydrogen production, however, faces challenges in ensuring eco-friendliness and cost-effectiveness, especially when derived from fossil fuels. In this context, bioelectrochemical system or BES have emerged as a promising alternative for green hydrogen production. Among these, microbial electrolysis cells or MEC stand out for their ability to leverage biological and electrochemical process to produce hydrogen from organic matter under mild conditions. MECs operate by utilizing electroactive microorganisms to catalyze the degradation of organic substrate, generating protons and electrons. When a small external voltage is applied, these components drive the production of hydrogen gas at the cathode. This innovative approach not only offers a sustainable pathway for hydrogen production, but also aligns with waste-to-energy paradigms by converting organic waste into valuable energy resource.
Hello, I'm NAQIUDDIN. Today, I'm excited to dive into the theoretical background of hydrogen production and its revolutionary integration with bioelectrochemical systems. We all know hydrogen is a clean and powerful energy carrier, but how do we produce it in a way that's both sustainable and practical? Let's explore the answers together, starting with the method of hydrogen production. Hydrogen can be produced in three main ways: chemical, biological, and electrochemical methods. First, chemical methods, like steam method reforming, dominate current hydrogen productions. They are efficient, but here's the catch. They come with a hefty environmental cost in the form of high CO2 emissions. Next, we have biological methods, which rely on microbial fermentation or photobiological processes. These methods are eco-friendly, but struggle with scalability and low yields. Lastly, there's electrochemical production, such as electrolysis powered by renewable energy. This method offers the cleanest route, but it is often limited by high energy requirements and costs. Each method has its strengths and challenges, but what if we could combine the best aspect of biology and electrochemistry? That's where bioelectrochemical systems come in. Bioelectrochemical systems, or BES, are an innovative solution that bridges biology and engineering. In simple terms, they are systems where microorganisms drive electrochemical reactions to convert organic waste into valuable outputs like hydrogen. Here's how they work. At the anode, microorganisms oxidize organic matter, releasing electrons. These electrons flow through an external circuit to the cathode, where they reduce protons, generating hydrogen gas. The beauty of BES is their versatility. Not only can they generate hydrogen, but they also help in wastewater treatment. It's a win-win solution for energy and environmental sustainability.
Next, I will dive deeper into microbial electrolysis cells, MECs. MECs consist of three main components: the anode, the cathode, and a separator. These components work together to facilitate the production of hydrogen or other valuable byproducts through bioelectrochemical processes. To begin, let's talk about the material used in MECs. For the anode, studies suggest that the most suitable material include carbon-based substances, stainless steel, and a metallic anodes. These materials support microbial growth and facilitate electron transfer efficiently. For the cathode, ideal material include platinum, stainless steel, cobalt-based material, and nickel. These materials are highly effective in reducing protons and facilitating the production of hydrogen gas. Now, moving on to the types of MECs, there are two main configurations: single chamber and two-chamber MECs. A two-chamber MEC consists of two separated components separated by a proton exchange membrane. This setup is primarily used when high protein hydrogen production is required, as the membrane prevents mixing of gases. On the other hand, a single-chamber MEC does not have a membrane or separator. This design is commonly applied in wastewater treatment and hydrogen production, where gas purity is less critical. Both configurations serve different purposes depending on the application and desired outcomes. Next, let me explain the principle behind MECs. The process begins with active microbes growing on the surface of the anode. These microbes break down organic matter, producing carbon dioxide, electrons, and protons as byproduct. The electrons are transferred through an external electrical circuit, while the proton migrate through the electrolyte, as shown in figure on the right. This movement of electrons generates an electrical current that powers the system. When the electrons and protons reach the cathode, they combine with free protons in the solution to produce hydrogen gas. However, for this process to occur, an external voltage must be supplied to overcome the energy barrier for hydrogen production. This voltage, when combined with biological assisted conditions, ensure efficient operation and enable the production of hydrogen.
So I will explain how microbial electrolysis cells or MEC help in wastewater treatment by removing pollutants and enhancing water quality. First, MECs excel at removing organic pollutants. Wastewater is rich in organic compounds, which are broken down in the anode chamber of the MEC. A special bacteria called exoelectrogens metabolize these pollutants under anaerobic conditions. As they do so, they release carbon dioxide, electrons, and protons. This process effectively reduces the chemical oxygen demand, or COD, and biological oxygen demand, or BOD, which are two key measures of water pollution. By lowering COD and BOD, MECs significantly improve the water overall quality. Second, MECs can also handle nutrient removal. In the cathode chamber, reduction reactions take place. For instance, nitrates in the water are converted into nitrogen gas. Sulfates can be reduced to less harmful sulfides. This nutrient removal prevents problems like algal blooms, which are caused by excess nutrients entering natural water bodies. Third, MECs help with heavy metal and pathogen reduction. Certain heavy metals, like copper and chromium, can either be immobilized or recovered during the electrochemical reactions. This reduces their toxicity in the treated water. Furthermore, the anaerobic environment of the MEC, combined with its electrochemical processes, contributes to the inactivation of harmful pathogens, making the water safer for further use or discharge. In summary, MECs improve wastewater quality by breaking down organic pollutants, removing excess nutrient, and addressing toxic metals and pathogens. These capabilities make them an efficient and environmentally friendly solution for wastewater treatment.
Next, we move on to the applications of MECs in energy recovery. So, MECs are a revolutionary ways to recover energy from organic waste. Now, let's look at their two key applications in energy recovery. So, the first one is in hydrogen productions, where MECs can produce hydrogen gas, which is a clean and renewable fuel. They convert organic waste and wastewater into hydrogen gas through microbial activities that requiring less energy than traditional electrolysis method. This offers a sustainable way to generate hydrogen while managing waste efficiently. The second application is in the methane productions, where MECs can also enhance biogas productions by generating methane under specific conditions. By integrating MECs with anaerobic digestion systems, we can achieve higher energy recovery, making this a versatile solution for renewable energy productions.
Now I will talk about advantages and disadvantages of MECs. First, the advantages of MECs is higher energy recovery, where MECs can produce hydrogen gas through the process of electrolysis, which can be more efficient energy carrier compared to electricity. And second, utilization of low-value substrate. MECs can use low-value organic waste material, converting them into valuable product like hydrogen. And third, sustainable energy source. They are eco-friendly, contributing to sustainable energy solution will reduce carbon emission. Fourth, potential for biogas production. MECs can also facilitate uh, biogas production through the anaerobic digestion of organic matter. And fifth, flexible operation. MEC can operate at various scale from small unit to large installation. Move on to the disadvantages. MEC's dependence on external voltage. MECs require an external power sources to drive electrolysis, which can increase operational complexity and cost. Second, high operational cost. The cost associated with the material and technology can be high, limiting broader implementation. Third, electrode durability issues. As with MFCs, the durability and efficiency of electrode can be concerned, impacting long-term performance. Fourth, low current density. MECs may experience lower current densities compared to more conventional energy generation methods. And lastly, microbial performance variability. The efficiency depend heavily on the microbial community used, which can be variable and may require monitoring and control.
I would like to present a case study in Kingdom Saudi Arabia about the microbial electrolysis cell for hydrogen production and urban wastewater. In last few decades, Kingdom of Saudi Arabia has witnessed highest urban growth in Arabian region due to a drastic increase in the population and economic growth, which lead to great pressure on the current and future Kingdom of Saudi Arabia's energy and wastewater services demand. So the expansion of wastewater services and the use of treatment wastewater is gaining popularity in the Kingdom of Saudi Arabia as a viable source to bridge the water demand supply gap. As a result, there was a huge potential to develop a microbial electrolysis cell technology in the wastewater treatment, and it also able to produce energy as the current electricity demand of Kingdom Saudi Arabia is around 55 gigawatt electricity, which is increasing significantly every year at a rate of 5.8% and is expected to surpass to 120 gigawatt electricity by 2032. A study also has been conducted by the author. The amount of energy they are able to recover through the Kingdom Saudi Arabia wastewater treatment by the microbial electrolysis cell was a total of 1.52 times 10 to the power 13 kilojoules of energy. Lastly, many studies has been conducted that show the microbial electrolysis cell technology able to remove up to 60% of chemical oxygen demand from the wastewater and able to reduce carbon emission from wastewater treatment processes.
As conclusion, microbial electrolysis cells or MECs offer a sustainable method for hydrogen production, converting organic waste into clean energy with lower energy input than traditional electrolysis. They also contribute to wastewater treatment by removing pollutants and recovering valuable resources. While MEC provide advantages like high energy recovery and flexible operation, challenges such as external voltage dependence, high costs, and microbial variability remain. Further research is essential to enhance efficiency and scalability, making MEC a viable solution for renewable hydrogen production and a sustainable energy future. That's all